Hello everyone, this is Dr. Hopkins recording the next in our series of videos for 472. And in the last video we introduced the concept, or we introduced the second law of thermodynamics, which gives us a new state function, entropy. And in this video we're going to be very heavy in terms of equations and relationships. So we're going to relate entropy to everything that has come before us, so everything that we had in first law. Alright, so let's relate to our two state functions, internal energy and enthalpy. And so we'll start with internal energy. So we have our first definition of entropy is just the heat reversible over T. We know that the change in internal energy is just the heat plus work. It's a state function, so we can define that heat and work in terms of reversible, right? Because it doesn't matter the path for du. Individually, they are path functions, but together they form a state function. That's what the internal energy is. And so then we can just manipulate this equation. That's T ds. And then we can rewrite, so our change in entropy is just du over T minus work reversible over T. Okay, so it's a useful or potentially useful equation. Now let's do the same thing for enthalpy. And now the definition of enthalpy allows us to have U plus PV or du plus PdV plus VdP. We substitute what we did for du above in here, and then we have work reversible PdV plus VdP. This is very general, and then we redefine it in terms of S. Okay, so we haven't made any kind of assumptions that our work is PV work only in this case. Okay. So then we go to the next page and let's start with the differential for U. It can be CVdT and then this partial derivative. For an ideal gas, this partial derivative is 0. We've already kind of worked with that. And so then we take from our last equation, we take ds, we plug this in for du, right? And we're left with this expression. Now we're going to declare PV work only. Right, so now we get rid of, so we have our work reversible is just going to be minus PdV. So this is this quantity plus dV. And so then this could be a partial derivative. This is from equation of state. And then we can also relate to our two mechanical properties, alpha and kappa, that we can measure. And we do the same thing for H. We have our differential equation for H in terms of T and P. So notice we expanded that one T and V. We always do that for U. We always do this for H, because that's kind of the natural variables for those two. Actually, it's the whole reason why we introduced enthalpy in the first place. So then we do the same thing. We end up with an entropy term expanded out. We still have this dW prime. That's non-PV work. Okay, so if we now cut to PV work only, we get rid of that last term, right? So non-PV work goes away. And we're left with Cp dt. We have this can be determined from an equation of state, dp, and 1 over t here. And then we can also relate in terms of our mechanical properties. Okay, so then let's expand. So we've expanded U and H in terms of differentials. Let's expand S in terms of differentials. So entropy doesn't have any natural, so it doesn't have to be just expanded in terms of T and V. We can expand it in any ones we want. We can expand it in V and P. But right now we've expanded in terms of T and V, right? So matching kind of the internal energy. And so that means this partial derivative, CV over T, because we've defined that on the previous page. This partial derivative, if we determine it in terms of our mechanical properties, is this. Otherwise, it would be the derived from the quantity that we could get from an equation of state. If we expand it in terms of T and P, so naturally with respect to H, so then this is Cp over T, and then this quantity, so if the partial derivative of S with respect to P is minus alpha V. So here we have entropy changes with temperature change is related to the heat capacity over temperature at constant volume or at constant pressure. We will use that as we go along. Okay, so then we have all of these different expressions for entropy, and any of them, they're all equal, right? If we're looking at ds, they are all equal, But what we're really interested in is what happens to the entropy if we do a process, right? So we're all about evaluating processes in thermodynamics, particularly chemical processes. So if we do an isochoric process, we make dV equal to 0, and we integrate, we end up, this would be our entropy. Isobaric, we use the second term in our differential, make dP equals 0, that is the entropy. If it's isothermal, we have two different expressions in terms of our mechanical properties or in terms of our equation of state, which I have not related here, but you would have to derive back from a couple slides ago. And then we have the special case of reversible adiabatic. So that's the case where Q is equal to 0. In that case, delta S is equal to 0. We have no entropy change. All right. And then we have a couple of special processes which we haven't talked about yet, and we will get to as we start evaluating how we start using all of these first and second law principles to evaluate systems. So in a phase change, the delta S is the entropy of that particular change. So if this is melting, that would be the heat of melting or the enthalpy of melting divided by whatever temperature it melts, right, at constant pressure. Or if we're doing our melting at or our boiling or whatever phase change it is, or a solid-solid phase change, if we're doing it at constant volume, then it's the internal energy change of that particular phase change divided by the actual temperature itself. So these are phase transitions, which we'll do a little bit more later in the course. And then a constant energy process where we have no change in our internal energy, then our delta S is equal to this. We would derive that. And so those are all of the kind of expressions that we'll use to determine entropy for various processes. We have multiple equations, so it's not just, we have multiple equations for U, H, and S that you can use in any situation, and you have to practice choosing which equation is important under which problem. So until next time.